Dear students, I am Suresh Agarwal, Professor in the Department of Business Economics, University of Delhi. Today we are going to learn about regression and correlation and the method of least squares. Let us try to see what we would learn in this module. You would learn about the concept of regression analysis and correlation analysis, their concepts in two-variable regression analysis, the concept of population regression function, the sample regression function, and estimation of regression coefficients. We would also try to learn in this context ordinary least square method and the calculation of sample regression coefficients using OLS. We would also like to learn about the assumptions of linear regression model, and then we would summarize about what we have learned. Let me try to introduce the concept of the regression function. So let us start by considering a hypothetical example wherein a manufacturer of a particular make of soft drinks is interested in knowing the demand for its product during different months of the year that witness different temperature levels. It is very important for him to know the exact demand for its product as he operates in a highly competitive market. He realizes that if he overestimates the demand, he will have to stock costly inventory, and if he underestimates, then competitors can take over his market share. What should he do in such a situation? All he knows with certainty is that the sales of his product vary with temperature levels. The higher the temperature, more are his sales likely to be. His problem is that of predicting trends in his sales. Regression analysis and correlation are two vital tools that can help him in such a scenario to solve his business problem. In fact, if we are able to build in some functional relationship between the two variables, say x and y, where y is the unknown variable and x is the known variable. Let's say if we are able to state y is as a function of x, which is denoted as y is equal to fx. Then regression analysis helps us to predict the average or most probable value of y for a given x. In other words, going back to our example, the soft drink manufacturer knows y is the sales of his product, which is a positive function of the temperature that may be expressed in degrees of centigrade 0 C or degree C. So the temperature is our known variable x. Further, if the past trend in sales and temperature are known, one can easily use regression analysis to predict sales y given any value of temperature x forecasted for the future. Correlation analysis, however, helps us to study the extent, degree, or strength of the relationship that exists between y and x without stating the exact functional relationship between y and x. Y in common parlance is also known as the dependent or explained variable or a regressant. X is in turn is called either an independent or explanatory variable or a regressor. If there is only one explanatory variable known, it is a case of simple regression. As in our example, we can write down y as a function of x, where y is soft drink sales and x is temperature. However, if y is assumed to be dependent upon several, that is more than one explanatory variable, then it is a case of multiple regression, which can be expressed as y equal to function of x1, x2, x3, so on, where y could be the rent of a house, x1 is the area of the house, x2 is the number of bedrooms, x3 is the number of bathrooms. Here rent of a house depends upon more than one explanatory variable, namely the area, number of bedrooms and the number of bathrooms. Regression analysis was first studied by Sir Francis Galton, who tried to study a relationship between the age of the children and the age of their parents, and also the heights of the children and the height of their parents. The former, the height of the children being the dependent and the latter being the independent variable. He interestingly found that height of children of abnormally tall parents regressed towards some average value, which means they were comparatively shorter than their parents in terms of height. Further, heights of children with abnormally short parents again tended to move towards some average value of the population. In other words, they were slightly taller than their parents. This movement towards the average value explains the very concept of regression. So what is the concept of regression? Let us learn in this third section. Section 3, Regression Analysis Concepts. Let us try to learn some of the concepts in regression analysis. First, 3.1 is two-variable regression analysis. Let us take an example where wages of employees is considered to be a function of their number of years of education for 10 individuals. Here y is a function of x, where y is equal to wages in rupees in 1000 and x is the number of years of education in years. So if we have the table enumerating the employees' income and or the wages and their years of education, for 10 employees are given, this data is given in your table 1, I'm sure you can see this on your screens. We can now plot the above data in the form of a scatter diagram, and we can show this diagram in our figure 1. On the x-axis we have years of education, x. On the y-axis we have wages in thousands in rupees, which is y variable. You can see we have the scattered points, and then we have plotted a line for these scattered points. So we have a scatter between wages and years of education. Regression line is the line of best fit that passes through these scatter points as shown in this figure. We therefore would be interested in knowing how we get this line and the logic behind it. That is, we wish to both graphically and algebraically derive the regression line. So let us look at this section where we try to understand the population regression function PRF. We must understand that the data we have used in table 1 is a sample data. However, if the population is known, which means population here would mean all working people in a state or region or country, as the case may be, it is quite possible that for a fixed value of x, say 3 years of education, there may be an entire subpopulation, which means more than one individual, having different wage levels y. Therefore, if we arbitrarily fix 5 values of number of years of education x at 3, 6, 9, 12 and 15 years, there would be 5 subpopulations of y as shown below in our diagram. We have the 3 years, 6 years, 9 years, 12 years and 15 years school of education fixed. In this we can see that each of the subpopulation has a mean or expected value denoted by E into y upon x, that is expected value of y given x as shown by rounded dots. If we join these dots, we get a population regression curve. This curve shows that the expected value of y given xi, where I takes the value 3, 6, 9, 12, 15, is a function of xi. That means as xi increases, the expected value of y given xi, shown by dark circles, also increases. So expected value of y given xi is a function of xi. If we assume that the functional relationship between the two variables y and x is linear, linearity is often assumed for the sake of simplicity, then the population regression function PRF is stated as expected value of y given xi equal to beta 0 plus beta 1 xi. The above relationship is described by two parameters beta 0 and beta 1, where beta 0 is the intercept term and beta 1 is the slope term. Beta 0 depicts the average value of wages an employee gets if his number of years of education is 0, which means if xi is equal to 0. In other words, it is the wage an uneducated person gets. Similarly, beta 1 mathematically shows that the change in y when x changes by 1 unit, that is the amount by which wages change as the education increases by 1 year. This is also known as slope. So please note that linearity here implies linear in parameters beta 0 and beta 1 in this case. Let us now consider years of education to be, say, 6 years, that is x is equal to 6. While we consider the subpopulation of y when x is equal to 6, we see that not all individuals who have 6 years of education earn the same wages. Their wage levels differ, suggesting that there could be other factors apart from years of education that affect wages. If you think about it, it sounds logical, as wages may depend upon other factors like years of experience, gender, etc. Therefore, the difference between actual value of y, which is yi, and the estimated or expected value of y is a stochastic or random error term. Therefore, actual value of y, yi wage, can be said to be made up of two components, the estimated or expected value, which can be written as expected value of y given x equal to xi, that is shown by the regression line, and an error term depicted by mu I or mu. Therefore, yi is equal to expected value of y given xi plus mu I. Yi therefore is equal to beta 0 plus beta 1 xi plus mu I, or mu I is nothing but yi minus expected value of y given xi. The error term is hence the deviation of the actual level of wages from its mean or expected level at a given value of x, that is years of education. We can hence conclude that an individual's wages, the dependent variable, is made up of two components. The deterministic component, represented by expected value of y given x, that is expected value of y given xi, and the random component mu I. In fact, in all social sciences, the role of this random component cannot be undermined, as it is a proxy for all those variables which affect y, for example wages in this case, but have not been taken into analysis for some reason or one reason or the other. In the field of science, however, the relationship between variables is exact, and hence the observed values of the dependent variable can be accurately predicted through the regression line. Section 3.3, sample regression function or SRF. In real life, however, it is impossible to have data on the whole population, and therefore, or most often, a sample is collected. A sample is a representative picked up from the population data as shown in table 1. It is from this sample that a sample regression function or SRF is estimated. The sample regression function in turn helps to predict the population regression function, and the SRF is distinguished from the population regression function and is written as yi is equal to b0 plus b1 xi plus ei, or yi hat plus ei is equal to yi, where yi hat is equal to b0 plus b1 xi. So yi hat is the estimated value of y, which can be written as expected value of y given x equal to xi. b0 is the estimator for beta 0, the intercept term, and beta 1 is the estimator for beta 1, the slope term. ei is the sample error term, the counterpart of mu I in sample regression function. Therefore, in regression analysis, as discussed above, we wish to predict the population regression function, that is yi is equal to beta 0 plus beta 1 xi plus mu I, from the sample regression function, which is yi is equal to b0 plus b1 xi plus ei. The idea of constructing regression lines through the same data is that it is the line of best fit. This line, where the dependent variable is y, is the independent variable x, is known as y on regression line. However, if it were the other way around, we had taken x to be the dependent and y to be the independent variable, then the regression line would be called the x on y regression line. So we have the fitted regression line in this diagram, which is fitted regression line with residuals. So in continuation with the data in table 1 and figure 1, we observe that when x is equal to x2 is equal to 7, expected value of y given xi equal to 7, as shown by the fitted regression line, is equal to 58.29119, whereas the observed or actual value of yi is given in the table is equal to 70. The error term E2 is equal to yi minus yi hat, and similarly values for E1 to E2, E3, E4 and so on can also be calculated. The equation of fitted line, but the question remains that how do we algebraically calculate B0 and B1. The two most commonly used techniques of estimating the SRF are ordinary least square, which is known as OLS, and maximum likelihood method known as ML method or MLE, maximum likelihood estimation method. Let us now in section 4 look at estimation of regression coefficients. First, the ordinary least square method. The OLS method is by far the best method to estimate SRF, the sample regression function. The objective here is to choose B0 and B1 in such a way that residuals or deviations of actual values of y from their estimated values is as small as possible. That is, ei is equal to yi minus yi hat, or ei is equal to yi minus b0 minus b1 xi. We need to simultaneously minimize all residuals, that is E1, E2, E3, E4 and so on. So if we try to minimize sum of residuals, then some of them may cancel each other because they are opposite in sign. Figure 3 confirms this, as some values of y lie above the fitted regression line and some below it. Mathematically, we can show that the sum of the positive residuals is equal to the sum of the negative residuals, and therefore minimizing the sum of the residuals leads us nowhere. One another way is to minimize the sum of the squares of the residuals. That is, S is equal to E1 square plus E2 square plus E3 square plus E4 square and so on. On squaring the residual, we have two advantages. One, we are able to ignore the direction of deviations, and secondly, smaller deviations, and quite rightly so, are given lesser weight than larger deviations. Therefore, the objective of minimizing S, the sum of the squares of the deviations, becomes fruitful. Because of this reason, the technique is called the ordinary least square method. Let us now look at the mathematical derivation of regression line in section 4.1.1. Considering a general case of n observations in two variables x and y, where y is a function of x, then the fitted SRF is expressed as yi hat is equal to b0 plus b1 xi. The residual ei is defined as yi minus yi hat and is equal to yi minus b0 minus b1 xi. The OLS, we strive to minimize the sum of the squares of residuals S, depicted as S is equal to sigma ei square is equal to sigma yi minus b0 minus b1 xi whole square. To minimize S, we differentiate S with respect to b0 and b1 and equate it to 0. So, derivative of S with respect to b0 is equal to 2 sigma yi minus b0 minus b1 xi into minus 1 equal to 0. This is equal to derivative of S upon derivative of b0 equal to minus 2 into sigma yi minus b0 minus b1 xi equal to 0. This gives us sigma yi equal to nb0 minus b1 into sigma xi. This is our equation 1, or is also known as first normal equation. Derivative of S upon derivative of b1 is equal to 2 sigma yi minus b0 minus b1 xi into minus xi equal to 0. This is equal to 2 sigma xi into yi minus b0 minus b1 xi equal to 0. This on simplification is equal to sigma xi yi equal to b0 into sigma xi plus b1 into sigma xi square. This is our second normal equation. Solving 1 and 2 simultaneously, which means multiply equation 1 by xi and equation 2 by n, we get values of b1 and is equal to n into sigma xi yi minus sigma xi into sigma yi upon n into sigma xi square minus sigma xi whole square. This is our third equation. Dividing throughout by n, we get b1 equal to sigma xi yi minus n x bar y bar upon sigma xi square minus n x bar whole square. This we can denote as 3.1. Repeat, where x bar equal to sigma xi upon n and y bar equal to sigma yi by n. Also, xi or small xi is equal to capital Xi minus x bar, and similarly small yi is equal to capital Yi minus y bar. Then we can write sigma xi yi equal to sigma small xi plus x bar into small yi plus y bar, and is equal to sigma small xi yi plus n x bar y bar, as sigma xi small xi and sigma small yi is 0, because sum of the deviations from mean is always equal to 0. Therefore, sigma capital Xi square is equal to sigma xi plus x bar whole square, and is equal to sigma small xi square plus nx bar square. Substituting the values of sigma capital Xi yi and sigma capital Xi square from above in equation 3.1, we get B1 is equal to sigma small xi small yi upon sigma small xi square, which is our equation 4. So this is the value of the slope coefficient in the deviation form. To get B0, we divide equation 1 by n, and we get sigma yi by n equal to B0 minus B1 into sigma capital Xi upon n, which gives us y bar equal to B0 plus B1 x bar, or B0 is equal to y bar minus B1 into x bar. This is our equation 5th. Now let us look at the calculation of the sample regression coefficients using OLS in this section 4.2. We have a table 2 which shows calculations of the example which we had discussed earlier. So we have the employees, we have their years of education as X, we have their wages as Y, and then we have calculated XY and X square X. So on calculation, we find that if you substitute these values of table 2 in equation 3, we get B1 and we get B2, and B1 comes out to be equal to 8.582375 on substitution, and substituting this value of B1 in equation 5, we get B0, and which is equal to 54 minus 8.5823 into 6.5, and comes out to be equal to minus 1.78544. Therefore, the equation of the SRF is equal to yi equal to minus 1.78544 plus 8.582375 xi, and we can write down this as our equation 6. So having learned the calculation of B0 and B1, let us try to understand what are the assumptions of the linear regression model in our section 5. So we have learned previously that in linear regression model, our objective is to calculate the SRF parameters B0 and B1 and use them to predict valid values of their population counterparts B0 and B1. This may be possible only if certain assumptions about the independent variable xi and the error term mu I as enumerated below are made. So these assumptions are: first, the model is linear. By a linear model, we mean the model as stated below is linear in parameters, that is beta 0, the intercept, and beta 1, the slope parameter. That is, for our population regression function, yi is equal to beta 0 plus beta 1 xi plus mu I, and both beta 0 and beta 1 are raised to power 1, that is, they are of the degree 1. The population regression function, however, may or may not be linear in the explanatory variables xi. For example, if we have a model where yi is equal to beta 0 plus beta 1 xi square plus mu I, this is also linear, but this is linear only in parameters and not in the explanatory variable xi. But if we have yi equal to beta 0 plus beta 1 xi raised to power beta 2 plus mu I, this is not linear. Now, there should be the sufficient variation in x values, that is, not all values of the explanatory variable should be same. This is our second assumption. Let us see what would happen if all the x values are the same. It is evident that the mean of these values would also be equal to x values, that is, x1 equal to x2 equal to xk is therefore giving us x bar, which is equal to nothing but the same values. Then we know from the discussion that b1 is equal to sigma xy or sigma xi yi upon sigma xi square, and b1 is nothing but therefore is equal to sigma xi yi upon sigma capital Xi minus x bar square. So as xi is equal to x bar, the denominator reduces to 0 and the slope coefficient cannot be computed. The third assumption is that the error term has 0 mean value, that is, expected value of mu I given xi is equal to 0, or expected value of mu I given xi is 0. Very clearly, it implies that for a given x value, there is a subpopulation of y values distributed in such a manner that sum of the positive deviations from the line of best fit is equal to the sum of the negative deviations. We can see it from this figure 4, where we are showing that sum of the positive deviations is equal to sum of the negative deviations for all values of x. In other words, as discussed earlier, the line of best fit passes through the mean values of y for each x value. The arithmetic mean has the property that states that the sum of the deviations from it are always 0. That is, sigma xi minus x bar is equal to 0. Also, it implies that all other variables that were not taken into analysis but are known to influence y and contained in the error term do not systematically affect the mean values of yi. It can be mathematically shown as follows. Let the PRF or the population regression function be yi is equal to beta 0 plus beta 1 xi plus mu I, and expected value of mu I is not equal to 0, or expected value of mu I is equal to let's say alpha. So let Vi is equal to mu I minus alpha. Then Yi is equal to beta 0 plus beta 1 xi plus Vi plus alpha by substituting the values of mu I in the population regression function. So Yi in that case is equal to beta 0 plus alpha plus beta 1 xi plus Vi. We have rearranged these terms. We can write down Yi is equal to beta plus beta 1 xi plus Vi, where beta now is equal to beta 0 plus alpha. So expected value of mu Vi is equal to expected value of mu I minus alpha. Hence, expected value of Vi is equal to expected value of mu I minus expected value of alpha. So expected value of Vi is equal to alpha minus alpha is equal to 0. The intercept takes in this particular equation the non-zero component of the error term, making its mean always 0. That is the implication of the introduction of the variable alpha in this case. Let us now look at the fourth assumption. The assumption is that the disturbance term is homoscedastic. This implies that the error term for each value of x is drawn from a population with constant variance. That is, variance of mu I given xi is equal to sigma square, or expected value of mu I minus expected value of mu I given xi whole square is equal to variance. As from assumption 3, expected value of mu I given xi is equal to 0, therefore variance is equal to expected value of mu I square and is equal to sigma square as per this assumption. The disturbance term having a constant positive variance for all values of x implies even the variance of y subpopulations for all x values in the same. So for all x values in the same. This assumption implies uniform distribution of y values about its mean for each value of the explanatory variables. Now we can see all this in our this figure 5, where we are showing conditional distribution of the disturbances for given values of x equal to xi. Now let us look at the assumption of the error terms are independently distributed. This assumption implies that the error term mu I is independently distributed of mu j for all I not equal to j. That is, there is no autocorrelation or systematic association between the error terms for different values of the explanatory variable x. This, in other words, means covariance between mu I and mu j is equal to 0, which can be written as covariance mu I mu j is equal to expected value of mu I minus expected value of mu I given xi into mu j minus expected value of mu I given xj. This is equal to expected value of mu I mu j, because expected value of mu I given xi is equal to expected value of mu j given xj is equal to 0 because of assumption 3. This can be rewritten as expected value of mu I mu j, which is covariance, is equal to expected value of mu I into expected value of mu j, as the two mu I and mu j are independently distributed. The same is evident from figure 5 below, which is in continuation with our data of table 1. The error terms obtained as the difference between the actual y and estimated y values show no systematic pattern. That is the implication of this assumption of zero covariance. So if you plot the residual values, where we have on the x-axis the years of education, on the y-axis residual, then we can have a look at the pattern which is showing in this diagram. The sixth assumption is that the error term is assumed to be random and normally distributed around the population regression line. This assumption is vital because if the error term is normally distributed, the regression coefficients B0 and B1 would also be normally distributed, which will then be useful in estimating population parameters B0 and B1 by making it possible to conduct a whole gamut of T, F and chi-square tests. But let me clarify that this assumption of normality is not required for estimation, but is required only for inference purposes. So let us summarize what we have learned in this module. We have learned that regression analysis is based on the premise that there is statistical dependence of one variable on the other. We have also learned that regression analysis is a very vital tool that helps to predict the value of a dependent variable given the value of an independent analysis. In social sciences, relationship between two variables is seldom perfect. Therefore, we use a stochastic error or disturbance term as a proxy for all those variables that affect the dependent variable but could not be accounted for in the explanatory variables. We have learned that the population regression function is a concept that is near perfection. It is not possible to construct it because of the inability to access the whole population. Therefore, we use a stochastic sample regression function to predict the population regression function or PRF. We have learned the OLS technique is by far the best method to estimate the parameters of the sample regression function. Here we try to minimize the sum of the squares of the residuals. In order to estimate PRF from SRF, we need to make certain assumptions about the explanatory variable xi and the error term mu I. Thank you.